Hello everyone, welcome back to my channel. So in today's video, we're gonna return back to our Aspen Energy Analyzer software and we're gonna explore the remaining features of the software. And for your information, this is the part 3 of the videos and will be the final part of this topic. And of course, maybe in the futures, I will try to return back to this software if there's a new piece of information, or maybe there is a new features that are available, or maybe I found several interesting papers, old papers, or maybe new papers that I think worthy to be highlighted in my channel. So yeah, without further ado, let's check out our design problem. As you know, I am still gonna use the same design problem that I have used in my first two videos, part one of the videos as well as part two of the videos. So if you haven't checked out my earlier videos, please check them out. And as you can see in this slide, we are still gonna use the four stream design problem where the first two stream are stream number one and stream number two will be a hot stream, and then stream number three and four, the remaining two stream will be my cold stream. And we're still gonna use our cooling water default condition provided by the software as our cold utility, and we're going to use high pressure steam, HP steam, default condition provided by the software as our hot utility. And of course, we're going to use delta T minimum, as you can see here, of 10 degrees Celsius. But if you decide you want to use a different delta T minimum, different hot utility and different cool utility, as long as they are working fine, then by all means proceed. There are not much to talk about in this slide, but the only thing that I would like to highlight here is this table. Maybe this is not really a highlight. I guess this is more of me refreshing your memories. So as you can see here, on the first column, we have the CP values for hot and cold stream. The second portion of the second column here is basically the energy needed for heating up or energy that need to be removed for cold stream. And then of course the last column here is basically telling you how much heat that need to be removed or added above the pinch point, which is, as you can see here, hot pinch is 90 degrees Celsius and 80 degrees Celsius is just my cold pinch. Um, um, Another that I also would like to highlight here is in our Aspen Energy Analyzer, we have designed them. If you remember, we have attempted to create our own hand design, heat exchanger network design manually. As you can see here, as you can see on the images here, this is what we did in my second part of the video. So if you do, to those who haven't checked my earlier videos, please check them out. So yeah, in Aspen Energy Analyzer, they have, if you want to create your own energy heat exchanger network manually, you can use Aspen Energy Analyzer and you can simply create them, no problem. But in this video, I'm gonna show you a feature where you can ask the software to solve or to recommend you a 10 or more design that are possible for your four stream design problem. And another thing that I would like to highlight here is I also would like to introduce you with the forbidden match features. Okay, I will explain this later, but forbidden match is basically a scenario or a situation where two or more hot or cold and cold stream are prohibited to interact or exchange heat because of any process related issues, safety issues, or maybe just because people just don't want to have those interact. An example of this would be maybe a stream, one hot stream and one cold stream cannot interact because of maybe if they interact in heat exchangers, there's a possibility of a leakage, which can cause maybe explosion or fire due to reactivity of these species, especially when they are both mixed together. There are also a possibility that, contamination where, if there's a minor leak, it's very difficult to remove the contamination, or maybe because one of the stream, hot stream is available is in plant A of your area, and maybe the cold stream is located in plant B, in area B of your plant, which is like maybe a 400, maybe 1 kilometers away. Okay, this is just an example, so maybe where it doesn't seem to make sense, or maybe not even practical to have them exchange heat because they are so far away, and maybe there's an issue of pressure drop or stuff like that. It's basically two or more hot and cold stream are prohibited to interact or exchange heat because of any process related issues, or maybe someone just don't like these two stream to interact because of some weird reason, something like that. And of course, I also would like to introduce you with the network optimization features, where once you have selected the network that you like, maybe we can let the software further improve the design, in a sense that they can maybe further minimize their heat exchanger area, or maybe they can further minimize total annualized cost. And of course, how can they do that? They have their own constraint, and what they can do is they can simply vary the heat load for each heat exchanger, or maybe split ratio if they have a split a strip, something like that. I think I have covered all in the introduction section. So yeah, let's go to our Aspen Energy Analyzer, a software. All right, guys, as you can see, this is my Aspen Energy Analyzer software that I have just opened. Now, if you remember, I have created a file in my when I attempted to create my own heat exchanger network manually. So please check out my second part of my videos for further details. But basically, what I'm trying to do here is I don't want to begin from scratch. Well, of course, I can begin from scratch, just basically specifying everything, but I don't want to do that because it's just a waste of my time and also a waste of your time. So what I'm going to do is I'm just going to simply open my old file and then just begin or maybe continue from there. So what I'm going to do is I'm going to go to managers, go to heat integration managers. As you can see here, I have HIP1, heat integration project 1, basically a project or a file or maybe a scenario that I have created in my earlier videos. So what I'm going to do is click view. Now this will pop up, basically nothing, but if you click here, I have scenario 1. So if I click scenario 1, this, let me expand this, maybe let me make this one smaller. So as you can see, this is all of the information that I have specified in my earlier videos. All of this information are the same information for this. I'm going to use the same information for this video as well. Of course, these are my process stream. This is my composite curve. This is my utility stream, cooling water, high pressure stream. I have specified all in my earlier videos. So I don't want to begin from scratch. So what I'm going to do next is I'm just going to simply create a twin, basically a clone of this. So click this one, right click, clone scenario. So I will insert a new scenario name, maybe scenario 2. Hit enter and then click clone. Now, as you can see, but before that, let me expand scenario. In scenario 1, I still have design 1. If you remember, design 1 is basically my design, heat exchanger design that I have created manually in my earlier videos. Okay. But in my scenario number 2, I clone my design, my old design, as well as the scenario as well. So what I'm going to do is I'm going to click design 1. I'm going to right click and then delete design. hit yes. So in my scenario 2, I only have this scenario, basically all of the stream information, but there are no design. Okay, now that I have that, I'm going to use scenario 2 and then create 10 different design. So how to do that? It's quite simple. DT minimum is still 10, not going to change anything. But before I do that, I'm going to click forbidden matches. Click. Now, as you can see, forbidden matches is, as I told you, is basically you add a new constraint where maybe certain stream cannot interact or basically are prohibited to interact with another stream, uh, hot and cold stream. So it can be more than one, it can be just one. But in this case, let me try to have a hot stream is prohibited to interact or exchange heat with a cold stream number one. So I click this guy. So this dialog box will pop up. Basically, they just simply tell you that I have chosen to forbid a match, meaning that my new design later proposed by Aspen Energy Analyzer will not have a hot stream 1 to be interact with C1 at all. Later we will see. So I hit OK. And then what I'm going to do is I'm going to click close. All right, next what I'm going to do that is quite simple. Just recommend design. Click recommend design. Now in here, the new box will pop up. The solver will try to propose maximum of 10 design. But sometimes, depending on the constraint, depending on the stream information, they may propose more than 10, maybe 5 or 4, depending on the constraint. And of course, these are just split branches. So in order to recommend a design, basically the solver will allow only 10 branches or 10 split for each stream. Normally it will be way less than that. And these are just a preview economic information. If you want to click, just click. Basically, these are the equation used to calculate the heat exchanger area or maybe fired heater if you use a fired heater as your utility. These are just your ROI, plant years, whatever. I'm not going to change any of this because this is not really the purpose of this video. So close. Forbidden match is the same. Basically, we have covered that earlier. Just to preview, this how we click. These are just a process stream, not that information utility stream, not that important as well. So what I'm going to do next is just click solve. So as you can see, when they click solve, they have generate 10 design. Okay. Now, just because they generate 10 design does not necessarily mean that all of the 10 design will be a correct design. So as you can see here, I have 10 design. So design 1 all the way to design number 10. Now, if you see here, this symbol has a white background, means that this symbol is technically, let me click. This symbol means this design technically is already solved. It's good to go. Same goes with design number 2, same goes with design number 3, 4, 5, and so on and so forth. Now, what about design number 7? They have the yellow background. So if you check here, you have this network has a yellow colored one. Means that there's something wrong with this heat exchanger that makes this a network just wrong or invisible. So what you can do is quite simple. Just double click. Now, once you have double click, you see here invisible heat exchanger. There is a temperature crossover, so CTH plot. So how to solve this? Let's say you like this design, but it just so happen that this design is invisible because of this heat exchanger. One way to solve this is quite simple. Just right click, delete. Now, once you have deleted this design, this heat exchanger, this become a dashed line. So you need to solve this manually. So what I'm going to do is just hit heat exchanger, left click, continue left click, move my cursor here, release, left click, and then release, right click, and then you left click, move to the cooler unit, and then you solve this design. Just hit tie, should be able to solve them. Then this one become white background. You can do the same for the design number 10 as well. We still have the same issues. You will see if you double click, um, it will tell you invisible. There's a temperature crossover as well. So again, I will do the same thing. Delete. There will be a portion of this stream is dashed line, so you need to solve them. So right click, continue right click, move your cursor here, release right click, left click, and then move it here, and then you double click, click tie, and then should be able to solve them. And one more thing that I would like to highlight here, maybe let me choose let's say I choose this design. If you remember forbidden matches, I forbid H1 to interact with C1. So if you see here, C1 is never interacting with this one is interacting with H1, which is a bit weird. It's not supposed to do that. So basically, this violate the forbid match kind of. It's kind of like violate the forbid match. This design violate the forbid match requirement. So let me check the other one. Well, C1 here is still interacting with H1, which is a bit funny though. Do I get it wrong? Let me check. I think no. I still have H1 still forbid with H1. Okay, again, I don't know why, but usually C1 is still interact with H1. Maybe because it just cannot do that. Yeah, maybe this one C1. Okay, this one may work. Okay, C1 never interact with H1 at all. But there are other design that interact with H1, which is a bit weird. But whatever, again, you have to check your design requirement and then whatever design proposed by the simulator. Sometimes it works, sometimes it doesn't. This one is C1 interact with H2 only. This one is C1 interact with H2. This one kind of makes sense. C1 only interact with H2. It doesn't interact with H1 whatsoever. What about this one? C1 is interact. Okay, in this case, they are still interact with H1. But whatever, again, you are the one who designed the network. It is you who need to be aware of your constraint. All right, moving on. Let's say I like this let's say I like this design and I would like to optimize them further. So what can I do? I click this guy, open optimization view. Now in here, if you see here, these are the performance of this particular design, heat exchanger design, where you have a network cost index, heating costs, cooling costs, capital costs, network performance in with regard to when compared to the ideal case. It's a 572% greater than the ideal case. So blah blah blah. Now area here is 278 square meters. So is there a way for me? So the question here is there a way for me to further minimize the area requirement of my heat exchanger network by varying the heat exchanger load, how much heat is for each heat exchanger, as well as if is it possible to have a much smaller or to further optimize the heat exchanger area by varying the split, so that's the split flow rates. So this is what it meant. So hit OK. They're gonna do a check. If all are checks, then you can click run. Not sure whether we have okay, they say optimization successful, and then they will create a design number 8, optima 8, and then dash O here means optimize. As you can see here, these are become invisible design. So sometimes it works, sometimes it doesn't. Maybe let me try the other design. It should have a split, by the way. Yeah, let me try this one. Okay. So here, 105.8 square meters. So if I do optimization where I try to further minimize the area, hit OK, run, let's see. Okay, it fails. Sometimes it works, sometimes it fails, but whatever. Okay, this is what. Okay, let me try design number 1. One last try. May work, it may not. So hit OK, run. Okay, this one, okay. So design one optimized. Now this one becoming a white background. So design one here, if you see, what I don't really know what are the things that they vary, by the way. So 3,000 still 3,000. So they probably something that they change. So you can go around and check. So as you can see here, the area here is 166.8 optimized. The one here is 187. So by varying the heat load and that heat exchanger, I'll say duty, then you can have a further reduction in total area. But of course, this comes at the expense of something else, maybe, which I don't know. So yeah, I think I have covered all, at the very least, the important features of this software from part one, from part two, part three. I hope you like it. All right, guys. If you like the videos, give it a thumbs up. Consider subscribing to my channel. I'm trying to make money here, so trying to make me motivated by watching longer videos, or maybe subscribing to my channel. I'll try to. I think next week I'm gonna upload videos on maybe mass integration, or maybe manually creating a heat exchanger network. Depending on the situation. A week after that, I'll try to find a new design problem for my Aspen. Again, I don't want to find a simple design problem because it's kind of a bit boring, I guess, at least for me. But if I find the research paper type design problem, it's kind of like too difficult for me to get it done in a week. Try to tweak it to make it work. So because it is a research paper, so it's gonna take time. But I will see what I can do. I think that's it for me. I will see you guys next video. Right? Bye bye and have a very nice day.